All right, so we have, first thing is I am going to be holding math lab hours today on Zoom from 1 to 4:30. And I'll send out the link for that after class sometime before 1. So you can look for that in an email. If you need help on your lab assignment or any homework problems, I'll be on Zoom. Tomorrow I'm going to have office hours from 8 to 9:30 a.m. And then next week we will have our virtual math lab open. We're in the kind of finishing stages of that. You probably before earlier this week, you probably actually got a message about joining it, because for some reason when we created when the class got created, it was created as published. So it is going to be unpublished, or it is unpublished right now, but when it is published, you should get an invitation to rejoin that. And there'll be some videos with help features about how everything will work in there. So you'll have more information about that as we move forward next week. The other thing I wanted to talk about was the lecture recording from the Tuesday video. So because of the overload in usage to the Zoom system with all the colleges and everything that are going on, that are using Zoom for their lecture, we are having some difficulty, or Zoom is having some difficulty in actually getting their recording thing to work in an efficient manner. So they say on their website they have engineers that are working on fixing that problem, but for the time being, my video is still waiting to be processed from Tuesday's meeting. So today's video, I'm actually recording right now, but I'm not recording to their cloud. I'm going to record just to my computer, and then later today I will upload that to YouTube and send you that link. And then of course, when Tuesday's meeting does become available, I will send the link out for that as well. Does anybody have any questions about any of the announcements? Okay, great. So let's go ahead and jump into the notes here. So you can see today we're going to cover section 15.2 and 15.3, hopefully. I am going to jump on the screen here. All right, so I just wanted to do a real quick review of what we did last time. So we started out by using double integrals to represent a volume under a surface, but we did it with these estimates. And one thing I wanted you to notice about this example here, the first one we did, and then the second example, is that the shape of the integration region R, see how that's R right there? R was from 0 to 4 and -1 to 2. That this was a rectangular region. In fact, that's why the region is called R. The R is for rectangle. It's not for region, it's for rectangle. Notice we had actually a square here, but a square is just a special case of a rectangle. Then we also had a rectangular region here. Then when we got to actually calculating these exactly using double integrals and not an estimator, we still were describing a region R. And notice for all these examples, our limits are all constants. Everybody see that? So like this example down here at the bottom of this page, the outside limit was constant 0 to 3, and the inside limit was constants -5 to 4. Everything is constants. We did this example where we talked about you could go both ways. You could do y first and then x, or you could do x first and then y. But again, notice the limits. The limits are all constants. And when the limits are all constants, that's when you're going to have a rectangular region. If the limits are constant, your region will always be rectangular. And the other things we talked about is, since according to Fubini's theorem, we have a choice to do y first and then x, or x first and then y. Pick the way that is the easiest. Don't choose the hardest method. In fact, sometimes one way may be impossible. And then the last case is when you have these types of limits that are constants, and when your function can be written as a function of x times a function of y, we can separate it out and do our integral with respect to x times our integral with respect to y. And so today we're going to deviate from these types of integrals, though, where we have a rectangular region where all our limits are constants, and we are going to talk about double integrals over general regions. Now, the nice thing about this is the concept is really still the same. We're finding the net volume between the surface and the xy plane. So if your surface is above the xy plane, you're going to have positive volume. If your surface is below the xy plane, you're going to have negative volume. But what's different is your region will no longer be rectangular. So, and we've actually already found areas for rectangular regions. You know, when we did the rectangular region, and yesterday, we found the area of the base by just taking length times width. Length times width gives you the area of a rectangle. But today it is a non-rectangular region. It will be a general region. So you can see this picture here. You can see there's a surface, the blue part that's stretched out over the surface. And then there's some general region. They're labeling it as a D, a general region D. And so what the double integral will give us is this volume in here that's between the xy plane over that little, I don't know, it kind of looks like a pinto bean or something like that, and up to the surface. So we're still going to find this by taking the area of the base times the height. Our height is the function, and our area of the base. And because this area of the base is non-rectangular, we have to use functions to find the area of that. Now, the good news is this is something that you've already done before. You did this in Calc 2 usually, right at the beginning of class, depending on the order that your teacher went over things. Usually you do it right at the beginning of the class. So like, for example, if we had let me grab my pen here real quick. If I had a region and say I had a parabola, y equals x squared plus 1. And then I had a line up here that was y equals 5. Do you all remember how we find the area between those two curves? Raise your hand in the, so if you go to participants on your window, you can choose to raise your hand if you think you know the answer to that. All right, Ian, how do we do it?
Where's my chat? Oh, hang on.
No,
So,
actually, you're talking. I can hear you.
oh, okay. Isn't it 5 minus x squared plus 1? Is that right?
Yeah, you have to subtract them. You take the top function minus the bottom function. Y'all remember that? Thank you, Ian. All right, so I can see some of you are said no, that's all right. It is a review thing. But yeah, if you wanted to find this red area here, what we did was in Calc 2, we learned that you take you take your bounds on the x-axis. So in this case, this red region goes from -2 on the x-axis to +2. And then you take your top function, which is this straight line, which is 5, minus the bottom function, which is the parabola. It's x squared plus 1. dx. Does that look familiar? Okay, so we are going to do the same thing for finding the area of the base, this D region down here. And really, you will remember from Calc 1, or I mean Calc 2, there's two different ways that this can be done. We can have what's called a type 1 region. So you can have a type 1 region where there is pretty much always a top function and a bottom function. And I have 3 different pictures down here of the way that could look. So, and when that is the case, we no longer have limits that are all constants. We have your x limit will be constants, but your y limits will be this bottom curve to this top curve. Now the key thing to remember here, so if I'm looking at this picture here, if I'm looking at this picture, you'll notice, and it's a little hard to see on my screen, but the bottom curve is g1 of x and the top curve is g2 of x. When you have a picture like this, does everybody agree that this is true? If the bottom curve is below the top curve, then we would say g1 is less than g2. All your y values are between that lower function and that upper function. Does that make sense? Okay. So what that means is that those functions are actually your limits. So this, your lower function, that's the lower limit. And then I'm going to say actually, rather than lower, I'm going to say bottom. Your bottom function is the lower limit, and then your top function is the upper limit. And again, this is something hopefully you did in Calc 2. And then while that's going on, you have, notice in this picture, you have x going between A and B. Now, one thing that's important to remember is that your constant limit, so go down here, this is how we would actually find the double integral. Your constant, your A to B, that's your x's, that is the outside limit, and it has to be that way. You need your functions on the inside and your x's, your constants on the outside. So this is your top function, and this is your bottom. Remember that the limits here, these integral symbols, line up with the dy and the dx on the back end. So this inside limit goes with y, and the outside limit from A to B goes with x. Same as last time. Does anybody have any questions about that? Yep, I can repeat that one more time. So we're trying to find this double integral, but the region, we're no longer having rectangular regions, we're having general regions D. So you have a picture of D here that has a bottom curve, G1, and a top curve, G2. This bottom curve is always less than this top curve when you're talking about the values of y. And so this bottom curve becomes the the lower limit of your inside integral, and the top curve becomes the upper limit of your inside integral. And then that inside integral symbol with the G1 and G2 as limits, that goes with your Y. And then the outside limits A to B goes with your X. Got it, Natalia? Okay, any other questions? And we'll do an example here in a second that will hopefully make this even easier to understand. The other thing is there's also type 2 regions. And you did these in Calc 2 as well. This is where instead of having a bottom and a top function, you have a right and a left function. So you have some function that's always on the left, and some other function that's always on the right. And again, if we're in the x direction, that right function will always be bigger than that left function. And so this type, the first one went from bottom to top on your integral. This one, your integral will go from left to right. And here is what that integral looks like. So now notice the order is switched. In the last one, it was dy dx. This is now dx dy, because remember the constants need to be on the outside, and then the functions need to be on the inside. So you might want to add here again, this is your left function, and then this is your right function. Any questions? I think, again, we're going to do an example here in a sec. Okay, so let's look at an example. Before we do that, I just want to say, again, this is the same concept as what we did last time, in that we have a function, which is our height, multiplied by the area of the base, which is our dx dy with these limits. So it's the same idea. So what you have here is, if you can picture this curve here, or these two curves that I'm boxing here, that curve is in the xy plane, or those sets of curves are in the xy plane. And then we have some function right here, we have some function xy that sits below or above the xy plane. And so what we're finding here is the volume between this area in the xy plane and the surface x plus 2y. Now, the only application of these that we've looked at so far is just volumes, but there's actually a lot of engineering applications to this that we will look at later in the chapter. We'll talk about how you can use it to find mass and center of mass and moment of inertia and things like that. And there's other applications too, but you'll probably focus a lot more on the other applications in your physics classes and some other classes, but we will do a few in this class. So let's talk about this one. If I could really emphasize this, and I'm going to repeat this throughout the day, always draw your region in the XY plane first. Really emphasize it. Lots of stars around it. Now I did the work for you here. Notice I already drew the picture, but you can use, Desmos or your graphing calculator to do this for you. So it's not like I have to do it for you. I just did this to save you time. But looking at that graph, we have two parabolas, and is it easy to tell which is the lower curve and which is the upper curve? Okay, Zach says yes. Everybody else agree? Can you just looking at that, can we tell which is on the bottom and which is on the top? All right. Okay, good. All right. So if I'm trying to find this double integral, x plus 2y dA, I need to first think about, is this a type 1 region or is it a type 2 region? Is this a region where I have a bottom curve and a top curve, or a left curve and a right curve? Yep. Yep, type 1, because I have this bottom and here top curve. So that means I want to make the order dy dx, because we need our x's to be on the outside. So if you're looking at this picture, the x's go from -1 to +1. I'm going to put those limits on the outside. And then for the inside, I'm going to put my lower limit should be the bottom curve, which is 2x squared. And my upper limit should be the top curve, which is 1 plus x squared. Any questions about that setup? Okay. And again, I just want to point out that the outside limit part, this outside, this -1 to 1 and 2x squared to 1 plus x squared with the dy dx, that's the area of this D region. When you multiply that by the x plus 2y, that's the height, and this gives you a volume. So let's evaluate this. Do we start on the inside or the outside? On the inside, yeah. We always start on the inside. So our inside integral is 2x squared to 1 plus x squared. And it's a little weird having functions there, but that's okay. So we have x plus 2y, and we're going to integrate this with respect to y. And when we do that, we're going to treat anything that is an x as a constant. So this x is a constant. So we talked about this last time. When you integrate a constant, you just add the y. So this will be x times y. Okay, and then the other one is a y. So when you integrate that, it becomes y squared over 2. And you already have that other 2 there, so this one becomes y squared. And then I'm going to apply the fundamental theorem of calculus to take this from 2x squared to 1 plus x squared. Questions about that? Am I going to plug in these limits here, the 1 plus x squared and the 2x squared? Am I going to plug them in for x or for y? In for y, yep. Okay. So when I plug those in for y, I'm going to have x times y, but y in that case is 1 plus x squared plus 1 plus x squared squared minus, now I'm going to plug in the lower limit. This is x times 2x squared plus 2x squared squared. And from there, it's really just algebra the rest of the way. Let me actually do an aside calculation here. We do have this part here. So let's do that on the side. This is a commonly messed up thing. Remember, this means 1 plus, oops, I wrote that wrong. That means 1 plus x squared times 1 plus x squared. Which is, of course, 1 plus 2x squared plus x to the 4th. So just kind of simplifying this out, I'm going to distribute the x there, and you get x plus x cubed. Then we just simplified the next part out. That came out to 1 plus 2x squared plus x to the 4th. We have minus 2x to the 3rd plus 4x to the 4th. And I'm going to pause there and ask if anybody has any questions. No questions? All right. Continuing on, I'm going to now collect like terms. Notice that there's a minus sign here, so you have to distribute that. So this is actually minus 2x cubed and minus 4x to the 4th. So I have x to the 4th minus 4x to the 4th is minus 3x to the 4th. I have x to the 3rd minus 2x to the 3rd is minus x to the 3rd. I have plus 2x squared. I have plus x, and I have plus 1. A nice clean integral there. All right, so notice that because we plugged in our inside limits first, we did our inside, which involved x. Now everything that started out with x's and y's, this x plus 2y, now everything is x. So now we can apply the outside integral, 1 to 1 of all this stuff. Negative 3x to the 4th minus x to the 3rd plus 2x squared plus x plus 1. We just start with our antiderivatives. So you have minus 3/5 x to the 5th minus 1/4 x to the 4th plus 2/3 x to the 3rd plus 1/2 x squared plus x, and that goes from -1 to 1. Are we good? Okay. So then we just apply the fundamental theorem of calculus and plug in the upper limit minus the lower limit, and we get minus 3/5 minus 1/4 plus 2/3 plus 1/2 plus 1 minus, now we plug in the -1, you get positive 3/5 minus 1/4 minus 2/3 plus 1/2 minus 1. And we got some things that are going to cancel out here. We're going to cancel out our 1/4, and we're going to cancel out our 1/2. So if you take all the stuff that's left, we have the minus 3/5 plus 2/3 plus 1 minus 3/5 plus 1, and this should come out to 32/15. This is a volume, so this is units cubed. All right, so there's our first example. Is there any questions about that? No questions? Okay. And again, I want you to notice my note at the bottom of the page. It says, when setting up any definite integral, such as the one in the last example, it is essential to do what? Draw a diagram. Always draw the diagram. What does it look like in the XY plane? And of course, I did that one for you, but you should be well adept at doing that. So, all right. So I have another example here. Notice there's no diagram given, so you're going to need to start with that. And what it says is to set up the double integral for 4xy minus y cubed dA, where d is the region that's bounded by y equals square root x and y equals x cubed. So you should graph both of those curves on one graph and get your region. And notice it's just set up, so we're not going to actually evaluate this one. We're just going to set up the bounds. And by the way, I mean, you saw how long that last problem was. I'm not going to have you do a ton of these on the test, just because the problems can be too long. There's a lot of the problems that we'll have on the next test will be just set up only. You don't have to worry about evaluating the whole thing. I will test you on that, but it won't be every problem. So I want to really focus in on how we set these up today so we can do more problems. And what I said here is I want you to set this up as two ways. So this one is actually a curve. Once you graph it, you'll see what I mean. You could treat it as a type 1 where you go from a bottom curve to a top curve, but you could also treat it as a type 2 where you go from a left curve to a right curve. So let's go ahead and do that. I want you to actually do this one on your own. So the first thing you should do is draw the region. So you can use your calculator, or Desmos, or whatever you want. Go ahead and draw what that region looks like. And then you're going to do it as a type 1, where you have a double integral of your function 4xy minus y cubed. It'll go dy dx. And then I also want you to do it as a type 2, where now you have the 4xy minus y cubed, but your inside limit is x, so you're going left to right. All right, so go ahead and try that on your own. I wish you could work with a person next to you, but that's a little hard to do. Question from Zach, it says, can't we just use constants for x and y? No, we can't, because this is not a rectangular region. You can only use constants if you have a rectangle. So just like that last example we did, this was not a rectangle, so we can't just use constants. The outside limits are constants, but the inside limits are going to be functions. They're either going to be a bottom to top function or a left to right function. Okay, so go ahead and try that. I'm going to give you a few minutes here to go ahead and see if you can set those up on your own. But again, first draw that region out. I'm going to step away for a second. I'll be right back. All right, so hopefully you have your graph going here. Let's make sure everybody has the right graph. So you have a curve that kind of goes like this. That's the curve y equals square root x. And then you have your cubic function, which is going to go like this. Of course, the cubic function also continues and comes down here, but they intersect. They intersect at this point 1, 1. And so our region that we're talking about here, our region D, is this stuff right in here. It's this area here. Did you all get that as your region for your graph? And I see Gabby asked the question, did you all change your bounds to be in terms of y for type 2? And yes, you have to do that because so in type 2, notice your inside limit here is x. And so this needs to be a x equals and a x equals for that inside bound. So that means for this curve, your y equals square root x. If you solve that for x, that's going to be x equals y squared. You have to square both sides. And then this other curve, which was y equals x cubed, that means x is going to be the cube root of y, right? To undo the cube, you got to take the cube root. Okay, so I'm going to give you just a little bit more time here. All right. So we're going to put these bounds on. Type 1 first. So this is y equals. This should be a bottom curve to a top curve. So my bottom curve is this one right down here, which is y equals x cubed. And then my top curve is the y equals square root x. Now notice as that's happening, x goes from 0 to 1. So your outside is constants. X is going, in fact, let me do this. So x is going from 0 to 1 as y goes from this bottom curve to this top curve. Right, so anybody have any questions about the first way? Okay, now the second one is going to be left to right. So we're going to be going from our left curve to our right curve as y goes from 0 to 1. And again, these bounds down here have to be in terms of y. which we already solved for. So my left curve is this one here, the y equals square root x, but it has to be in terms of y, so it's x equals y squared instead. That's my lower bound, y squared. And then my right bound is this right curve, which is x equals cube root y, as y goes from 0 to 1. All right. Talia says, on type 2, I never know which side is left and which side is right. Well, Natalia, can you see how I drew this green arrow in here? The green arrow is going from left to right. And so on the left side, where it touches here, this is the left side and then this is the right side. You just have to look at on that left side where that green arrow starts, what curve is that? And then on the right side where the green arrow ends, what curve is that? Does that help? Or do I need to try to explain it a different way? Okay. Any other questions? Yeah, so that's a good point. And I actually, when I teach this in class, I do the same thing, Gabby. So Gabby said, I find it easier to visualize the y-axis flipped like the x-axis. So it thinks of, you think about it as a top and a bottom. I can't do that with, oh, actually, maybe I can here. Just went like 20 pages ahead. Sorry. There you go. So if you flip your paper sideways, like I just did, you can think of it more as bottom to top, just like the type 1 region. So you can see now the arrow looks like it's going from bottom to top. And my bottom function is that x equals y squared function. Then my top function is the x equals cube root y. All right. So thanks for the reminder, Gabby. All right. Any other questions? Yes. Jessica asked, the left is always the lower limit and the bottom is always the lower limit. And then for the upper limit, it's always either the right or the top. So it's always for type 2, it's always left to right. And for type 1, it's always bottom to top. All right, any other questions? All right, let's do one more example here. I'm going to skip this one here and I'm going to move to page 75, the first example on page 75. So when we first started talking about double integrals, we talked about the fact that integration can be done in any order. One order is often easier than the other, and sometimes one order may even be impossible. We talked about that yesterday. And this is a case where we have that true. So let's look at so it says integrate the integral from 0 to 3 and x squared to 9 of x cubed e to the y cubed. And I want you to notice that this integral is not even possible for us to evaluate it. So if we did y first, then notice we have a function inside of a function. We have e to the y cubed, and in order to evaluate e to the y cubed dy, we would need to do a u substitution, which means we'd have to have a y squared in front. Because if I were to let u equal that inside function, the derivative of that is 3y squared. And so because of that, I need a y squared, and I don't have it. So this one, we can't even evaluate it. This is not possible to evaluate. But we can do it actually if we switch from a type 1 to a type 2. That's the cool thing. So this right now is type 1. How do we know that it is type 1? I said that, but how do we know that it's type 1? Yeah, because it's dy here. All the inside bounds are functions of x. That makes it a type 1. And so since it's a type 1, we are given on the inside bounds for x, I mean on the outside bounds for x and on the inside bounds for y. And our y bounds go from a lower limit of x squared to an upper limit of 9, and our x bounds go from a lower limit of x to an upper limit of 3. I'm just getting these directly from our integral symbol. And so any integral problem, double integral problem, what do we always want to do first? Think yes, draw a picture, draw a picture, draw a picture. I'm going to sound like a broken record today. So I'm going to draw a picture. And I'm going to start out with the curves for y. So remember, this is y. Y is always between y equals x squared and y equals 9. So I'm going to draw those curves. All right, so there's the curve y equals 9. And then we have the curve y equals x squared. We know 3 squared equals 9, so these are going to intersect at 3. So this is a parabola. So this goes from, notice x goes from 0 to 3. So it's not actually this full enclosed region. It's only from 0 to 3. So my region D is actually just like right-hand side here. Now that I've drawn it, hopefully you can see that my bottom curve is the x squared and my top curve is the line y equals 9. Now what we want to do is convert to a type 2 region, because we saw that type 1 was impossible. So for type 2, we still have the same function. We still have x cubed e to the y cubed. But now it's going to switch from dy dx to dx dy. And so now, another color here, now we're going to go from left to right. From left to right. So what is my left curve for that area? X equals, yeah, and remember it's always x equals because now it's dx. So that it's the y-axis, and the y-axis is x equals 0. So my left bound is 0. Okay, and then what's my right curve? Where does this green arrow end? What is that curve there? X equals what? So yeah, I saw a couple people said 3 here. It does go to 3, but remember our inside bounds need to be functions. They need to be curves. So our left curve is a line, x equals 0, and our right curve is not, it does go all the way to 3 in some place, only at the end here, but it doesn't go all the way to 3 along that whole curve. The right side changes value, so you can't just say it's a fixed number like 3. It has to be a curve. So it's x equals the square root of y, and that came from our equation y equals x squared. If you solve that for x, you get x equals the square root of y. So our upper bound is the square root of y. Does that make sense? Or as I saw, some people said y to the 1/2. That's okay too, if you write y to the 1/2. And then our y bounds, these are constants, are outside now. Remember, outside are always constants. So if I'm looking at this graph, my bottom, my lowest value for y is down here, is at 0, and then it goes all the way up to 9. We start down there at 0, and we go all the way to 9. So you're going to go for y, you're going to go from 0 to 9. So again, the key thing to remember is the x's always have to be functions. The inside limits have to be functions, and the outside limits are constants. And sometimes your function is a constant. I mean, anytime you have a straight line, that's why you had 0 down here for the lower limit on x. That's because the left side was a line. It was that y-axis. All right, so did anybody have any questions about converting? The key is the picture. If you can see the picture, it's easier to put in the limits. Any questions? Okay. All right, so I'm going to go ahead and evaluate this one now. This will show you an example of doing a U substitution. So if I start with my inside limit, and my inside one goes from 0 to square root y, and I have x cubed e to the y cubed dx. And we're integrating with respect to x, so anything with a y is a constant. So if it, for some of you, it might even help to just pull it out in front so we don't even worry about it. X cubed dx, because that e to the y cubed is a constant. So then we're just taking the antiderivative. The antiderivative of x to the third is 1/4 x to the 4th. We're going from 0 to root y. And then we plug in our bounds. So we have 1/4 e to the y cubed. And when you plug root y into x to the 4th, you get y squared. And when you plug 0 in, you get 0. So this is 1/4 y squared e to the y cubed. And remember when we first started, we said that was what we needed. We needed a y squared in there, and now we have that. So we can move to our outside integral from 0 to 9 of 1/4 y squared e to the y cubed dy. Any questions? All right, you let u equal y cubed. This du is 3y squared dy. Solve for dy. dy equals du over 3y squared. And so I have 1/4 times the integral of y squared e to the u, and my dy is now du over 3y squared. I'm going to change my bounds. My bounds started out as going from 0 to 9. But when I change to u is now whatever y is cubed. So we have 0 cubed. Then we have 9 cubed. What's 9 cubed? 729? Okay. Notice that my y squareds cancel here. And I have this 1/4 times this 1/3, so I have 1/12. I have e to the u going from 0 to 729. This is 1/2 times e to the 729 minus e to the 0. Anything raised to the 0 power is 1. So I have e to the 729 minus 1. Oh, I lost my 1 there. Thank you. 1/12. 1/12. That's because of the 1/4 times the 3 down here in the denominator. 1/4 times 1/3 is 1/12. So there's my answer. I know some of you really struggled with doing u substitutions on the integration quiz. I do have a document with like 30 worked out u substitution problems showing all the steps and the answers and everything. Would anybody be interested in that as a review document if I mailed it out to everyone? Okay. All right, so I'll go ahead and send that out. Sometimes it's nice just to look at problems worked out as kind of review. So I'll go ahead and send that out. And I think we're at 9:20, so let's go ahead and take a break until 9:30. And I'll be back at about 9:30. We'll pick this back up. We'll finish up this section, and then we'll start. I don't know if we'll get all the way through polar, but we'll start that. All right, we'll see you in a few minutes. All right, I'm back. I was just checking over my email. I didn't get a chance to look at my email before or after like 4 something yesterday, and I noticed there was more people that asked about the link for Tuesday's video. And I did talk about at the start of this class, but some people might have come in late. I just wanted to reiterate that the link to that video has not been processed yet by Zoom. And when I do get it, I will definitely send that out. Today's video I am downloading directly to my computer, and I'm going to upload it directly to my YouTube channel. So you should get that one definitely a lot faster. And I'm going to keep doing that for the time being, as long as Zoom is not working. So anyway, let's go ahead and pick back up here. So I would like you all to try one like the one that I just did, where you reverse the order of integration. So you have this, it says reverse the order of integration. The integral is the integral from 0 to 8 for x, and y cube root y to 2 for y of the square root of x to the fourth 1. So notice this is x equals, and this is x equals, because it's dx here, goes with the inside one. And so if you solve that for y, what would you have for y? What would y be equal to? Y would be equal to x cubed. Ian, what did you mean 8? Oh yeah, that would be the top value. So that would come into play with the graph. So your curves here though are x equals 2, you're graphing, and y equals x cubed. So go ahead, everybody go ahead please, and sketch that region we're talking about on your own. Go ahead and sketch what that region looks like. Now, this is dx, so this is type 2. So this is your left curve, and this is your right curve. Your right curve is x equals 2, and your left curve is y equals x cubed. So x cubed is my left, and x equals 2 is my right. So I'm starting on the left at this curve, and I'm moving to my right and stopping at x equals 2. So your region should be this little sliver here. So does that region look like a region that we could write as a type 1 region? From bottom to top, even though it was written from left to right? In other words, do we have a curve if we were going this way? If we were going from bottom to top, is there a curve that's always on the bottom and always on the right, on the top? Yeah. Our bottom curve is y equals 0, and our top curve is this y equals x squared, or x cubed, excuse me. So you can definitely rewrite this. Our original integral yes, Gabby, y equals 0, funny. Okay, so we have y equals 0. Excuse me. Let's rewrite this. Yeah, so our original problem was x equals 0 to x equals 2 as, I'm sorry, y equals 0. It'd help if I could write this right. It was covered up. Let me see here. There we go. All right, so yeah, it was x equals 0 to 8. X equals 0 to 8. Y from 0 to 8. X goes from cube root of y to 2. We have the square root of x to the 4th plus 1. This was dx dy. And we are going to rewrite this, same function, square root x to the 4th plus 1, but we're going to make this dy dx. And so my bottom function, we just said, was y equals 0. That was down here. Let me actually draw that in. Here's my bottom function. And then my top function, my top curve, is right there. So my top curve is x cubed, and while that's going on, x is going from 0 to what? Zero to 2. All right. So that is how you do these problems. But Brandon asked the question, if we wanted to change a function from a type 1 to a type 2, could we just rotate the graph 90 degrees, or would that mess something up? Well, I think the thing that's confusing about that is knowing which is your x-axis and your y-axis. So my outside bound, I mean, you definitely could kind of rotate it. If you rotated it 90 degrees to the left, you would, 90 degrees to the right. So rotate, what would that be, clockwise. You would see that x cubed was your top function and 0 was your bottom function. Just need to make sure that your bound for the outside, your x, is going from 0 to 2, because your x is going to seem like your y-axis. I don't know if that helps answering your question, Brandon. Okay. All right, so any other questions about that one? These first two sections of this chapter are kind of long. So I actually have one more example here that I want to cover. And this is more of an application. So all these other ones have just been focused on getting the idea down of how to write things as a type 1 or a type 2. This application is actually specifically saying find the volume of the solid that's enclosed by the plane 4x plus 2y plus z equals 10, and the coordinate planes. Use technology to find the region. Question from Ian. When there is a function as a limit to one of the integrals, does it always flip to upper bound from lower bound when reversing the integration order? I mean, the two that we just did, that happened. I hate to say always. I don't think I've looked at it in that sort of detail where, I mean, to say always, that would have to be something that's been proved. And I can't think of if I've seen an example where that doesn't happen. It does happen a lot. I don't really have a better answer for you on that one though, Ian, I'm sorry. You stumped me. Okay. So again, we want to find the volume that's enclosed by the plane and the coordinate planes. So what does it mean when we say coordinate planes? Yeah, it's the XY plane, the YZ plane, and the XZ plane. So we have a plane, and it's going to basically be chopped off by all three of the coordinate planes. And so I'm going to go ahead and sketch this. And the easiest way to sketch this is by finding the intercept. So if you found the x-intercept, the x-intercept would be what you'd get when you let y and z be 0. So in this equation, if you let y and z be 0, you get 4x equals 10, which means x equals 2.5. Right, you get 4x equals 10, and then x equals 2.5. And you could do the same thing for all the other intercepts. So to do the y-intercept, you let x and z be 0, which gives you 2y equals 10, which means y equals 5. And then the last one, to get the z-intercept, you let x and y equal 0, which gives you z equals 10. So I'm going to go ahead and graph that real quick. This is going to be a sketch in 3-dimensional space. X, Y, and Z. Bear with me while I do this. So our x-intercept was right there, 2.5, comma 0, comma 0. Y-intercept is right there, 0, 0, 0, 5, 0. Then our z-intercept was at 10. 0, 0, 10. So you get this like wedge. If you could picture this sheet of paper out in space, and it gets chopped off over here at the XZ plane and the YZ plane and the XY plane down below. And you have this volume inside here between the top surface. So this is really our height. Well, say our function is the surface, and the surface is 4x plus 2y plus z equals 10, but if we solve for z, we get 10 minus 4x minus 2y. That's what you get here. And then our area is this base down here. I always kind of like to talk about it as the shadow. It's what's underneath. The shadow is that area underneath the surface. And so if we were to, I mean, a lot of times I like to think of the best way of thinking about this is to actually redraw that in two-dimensional space. So here's my x-axis, here's my y-axis. On my x-axis, my intercept was at 2.5, and on my y-axis, my intercept was at 5. So I have that region there. And then what I want to do is I need to know the equation of that line. Y equals. What's the slope of that line? Is it negative or positive? Yeah, and it's actually, it's negative. Somebody wrote -2. So it's -2x, and then my y-intercept is 5. So that's an algebra problem. If you know 2 points, you should be able to find the slope. The slope comes out to -2x plus 5. And so this, you know, this is my region, and I can treat this as a type 1 region. This is type 1. You could also treat it as a type 2, but since I already have my equation written out as y equals, it's kind of easier to treat this as a type 1. So if we want to figure out this volume, we can figure out exactly using a double integral. My function is that plane. We already wrote it up here. It's 10 minus 4x minus 2y. And then we have dy dx. And for the dy dx, I'm just looking at this purple region here. This is the shadow that's underneath our wedge of the plane. And so my bottom curve is right down here. That's my bottom curve. It's y equals 0. And then my top curve is right there. That's -2x plus 5. I'm going from bottom to top. And while that's happening, my y's, or my x's are going from 0 to 2.5. So there's an application of double integrals where we're actually finding a volume. I'm going to skip the steps on evaluating because we've done a number of these already today. You know what? I don't have the answer to this one in front of me. That's probably the toughest one we've done. Does anybody have any questions about that? I think you have one like this in your homework you can give a shot at. All right. Well, if no one has any questions, then I am going to go ahead and jump into the last page, which has some properties. And really, I just want to talk about one thing on the last page that's probably the most important thing, and that is number 5. All right. So, and here's how it works. So, if I look at my, let me just rewrite a double integral like we've been talking about here. So remember that the dA part, that's the area of the base, and then the function is the height. And when you take the area of the base times the height, we get a volume. All right, so what happens if you let the height, or you let the height be equal to 1? So if you take 1 times the area, what do you get? You get the area. Yeah. So it's kind of a weird concept, but if you look in this picture over here on the right, we have this surface z equals 1. It's like our top curve. It's just the plane z equals 1. And we know that the double integral will describe this area down here, this d, the limits, our double integral limits with the dA. That's going to give us that area. Well, if we take that area and we multiply it by a height that's equal to 1, it's still equal to the area. When you multiply anything by 1, it doesn't change it. So whenever you take a double integral of a function that is 1, that actually gives you the area. Kind of an interesting application. Any questions about that? Okay. Units would be units squared. And we have a question here. We have to multiply the volume by the area every time. No, if we want to get the area of just the base, so we want to get the area of this shadow down here, this area D, you can do it by taking the double integral. But for the function, you know, normally, let me scroll back up. So normally we've had a function, like in this last one, we had a function of 10 minus 4x minus 2y. Here we had a function of the square root of x to the 4th plus 1. Every one that we've done so far has a function in there. Well, it turns out if you let the function be 1 and you calculate this integral, you don't get volume anymore, you get area. Does that make sense? So just to kind of summarize, if I have a double integral of a function dA, we know this gives us volume. A special case of that, though, is if we take that function, and if we let that function be just z equals 1, like in this picture, z equals 1, then you're going to be taking 1 times our area, which gives, and if you multiply 1 by anything, you don't change it, so you just get area. Okay. All right. Now we've been going through this, and some of these problems take a long time. My favorite problems in double integrals are those with polar coordinates. Polar coordinates are usually really integrals that are easy to find, and we're going to be using them a lot for the rest of the semester. So you want to have a good understanding of 15.3. Now, polar coordinates was probably first introduced to you in Calc 2. And we understood it in Calc 2 to be just another way of describing points in the XY plane. So anytime you have a point out here, X comma Y, we normally, throughout math, we think of how to get to that point by going over X and up Y. But then along comes polar coordinates, and polar coordinates says, wait a second, I can describe that same point P with an R and a theta by saying, okay, we have this ray R that goes from the origin out to the point. That ray has a length, and that ray is at an angle of theta, and you can describe the same point with an R and a theta. Now, because of the Pythagorean theorem, since this distance is x and this distance is y, we can say that r squared, the hypotenuse, is the same as x squared plus y squared. And then we've also talked about how to find the x and the y coordinates of our point P this semester using trig. So we said we could find the x by taking our hypotenuse r, or our magnitude, times the cosine of theta. And then we can find our y by taking r times, instead of cosine, times sine theta. I'm not going to go into the details of how we do that, because that's something we've already talked about this semester. We can talk about it during my office hours online or the math lab if you're interested in going into that a little bit more. But this is our conversions between how we go between x and y and r and theta. Now, these regions, this type of integral, double integrals in polar coordinates, only work well in circular regions. So if you notice, we have two circular type regions in the problem here below, or in the example below. And if I wanted to describe this whole area right here in the picture, I'm going to have some bounds that are going to need to be in place for theta and for r. So if you look at this picture, theta is going to be described the same way we think about in the unit circle. So theta is going to go since we have a full circle here, theta is going to go all the way around. So how many radians is that if we go all the way around a full circle? It's 2 pi. So our theta goes from 0 to 2 pi. And then likewise, our r now, our r is our distance from the origin. So r, if we want to fill in this whole area, r is going to go from 0 all the way out to the radius of that circle. What's the radius of that circle? It's 1. Yeah. And this is so much easier than the last section we just did, because we're just looking at, okay, well, what are the bounds for the radius? And you can usually just tell from the picture. And what are the bounds for theta? Does anybody have any questions about that first example in part A? Nobody has any questions? I'd like for you on your own to go ahead and write out what you think the bounds are then for R. Yep, so hopefully you got theta is only going halfway around the circle, so theta is going to go from 0 to pi. And then r, remember, circles have equation, the equation for a circle is x squared plus y squared equals r squared. So if r squared equals 4, that means r equals 2. If r squared equals 1, that means r equals 1. So this is going from 1 to 2 for r. All right, so questions about that. If you can do that, that's all you really need to know for finding limits with polar coordinates. It's really nice. Does anybody have any questions about that? All right, so let's do an example here. Oh, there's one thing I need to talk about in the box on the next page before we do an example. So this box here is a theorem, and it talks about how you convert from polar coordinates or from XY coordinates to polar coordinates. And notice that it kind of has a different notation for the function. All that says is that means write your function in terms of r and theta. And then notice for the dA gets changed too, and this is kind of interesting. The dA becomes RD theta. And this is one of my kind of corny math things I like to joke about. So my joke is always that pirates really like to do polar coordinates. Can you see why? Because what does a pirate say? Arr! RDR, matey! RD theta! Oh, I got one laugh out loud. Thank you, Ikram. I appreciate that. Yes. RDR. Pirates say RDR. So when you do a integral in polar coordinates, you have to, instead of dx dy, you have to not only put dr d theta, but you have to add a r. Sorry, some of you, I probably woke you up with my really loud RDR. Anyway, let's do an example. So I have this double integral. This is the double integral of 2xy dA. R is the portion of the region between the circles x squared plus y squared equals 4 and x squared plus y squared equals 25 that lies in the first quadrant. Ian, you can borrow some of my kids' pirate Legos. We got them floating around our house. Maybe I'll have to show it next class. I'll have to put it up. All right, what do we do first? What is the first thing? I should always teach in a pirate voice. I think my voice would hurt. What's the first thing that we should do whenever we do a double integral problem? Dry picture, matey. All right, so what are the radius of these two circles? Two and 5. All right, good. So we have a radius that goes from 2 to 5. So my inside circle has a radius of 2. And then my outside circle has a radius of 5. So I always think it's kind of nice here then that once you have your picture to write out what your bounds are for, just like we did on the first page, write out your bounds for r and theta. Go ahead and do that. Do we have a full circle? Mm-hmm. So hopefully you got that theta goes from 0 to 2 pi and r goes from 2 to 5. All right. And then I now want to try to evaluate this. So I had the integral of the region R, 2xy dA, and I want to convert that to polar coordinates. So remember, our function can't be in terms of x and y anymore. So we have 2 times x. And if you look back on the first page of your notes in this section, x was r cosine theta, and then y was r sine theta. And then my dA becomes r dr d theta. Oh, Ian just pointed out something I wasn't paying attention. I think I was so happy with my pirate voice. I was not reading the problem carefully. Anybody else notice that it said we were in the first quadrant here? So my picture, thank you, Ian, my picture was not very good here. It should have been just the first quadrant, which actually changes my bounds. My bounds should go from 0 to pi over 2. Thank you. So just to kind of label things here, this is x, this was y, and this was my dA. And the only other thing I have to put in there is my bounds, which we already have from the picture. My r, so r is on, dr is the inside, so my r goes from 2 to 5. And then my x goes from, or my theta goes from 0 to pi over 2. And I want you to notice here that all my bounds are constants, much like the first section we did, 15.1. So what can we do when all our bounds are constants? One thing you can do is swap the order. Let me go ahead and go back a few pages. Sorry, don't get dizzy from looking at this, but way back on the last page of 15.1, we had this theorem that said if we can write our function as a function of one variable times a function of the other, we can make this our double integral into the integral of one times the integral of the other. In other words, we can separate it. So we did that here. We did the integral of x times the integral of y squared. And with polar, you can almost always do that. You can almost always separate. So I'm going to do that because I can here. So I have a 2 constant. I'm going to pull the 2 out. And then the rest, we're going to separate it. Okay, so when we separate, I'm going to do the r's first. It doesn't really matter what order you do it. You can do any order. So notice we have an r, and then we have the r from the r dr. So we have an r cubed dr. And then we have another integral for the thetas, which goes from 0 to pi over 2, and that is sine theta cosine theta d theta. You can almost always do this with polar coordinates, which makes your integrals a whole lot more simple. All right, does anybody have any questions? Okay, what's your question, Ian? Yeah, so Ian's question is why we have to add that R for the dr and the d theta. And my answer to that question is it has to do with something that we're going to talk about at the end of the chapter. So the last section, I believe it's 15.9 or 15.10, we talk about changing variables, which is what we're doing here. And we have to calculate something that is called, what's it called? It's called, it fell out of my mind right now. Give me just a sec. The Jacobian, it's called the Jacobian. And it turns out in this case, the Jacobian for polar coordinates is R. And I'm going to show you how to calculate that. For right now, you just have to kind of take my word for it that every time you do a polar coordinate integral, you have to include the R. It's part of it. It has nothing to do with anything else in the problem. It has everything to do with the fact that we're changing variables. And anytime you change variables, there's a part that usually needs to be added. So yeah, I apologize if that's a little bit fuzzy. I promise we'll give more details about that as we progress through the chapter. I just don't want to throw that in there at the same time as also introducing polar coordinates. Is that all right? Okay. All right, very good then. So if I want to actually evaluate the second one, the second integral, how am I going to do that integral? A u sub, yeah. So we want to let u, I would probably do sine theta. That's going to be the easier one, but you could use cosine theta. Du then is going to be cosine theta d theta. And so that integral very nicely becomes the integral of u d theta, or not u d theta, u du. And if you change your bounds, we got to take the, Zach just asked if we can change it into sine 2 theta. Yes, you could do that as well. That's another way to do it. I generally just do the u sub, but yes, you could use the trig identity to change that because we have the 2 in the front and 2 sine theta cosine theta is equivalent to cosine, or not cosine, sine of 2 theta. I'm just going to do a u sub though. I'm going to change the bounds again, just like we've been doing. Our u is u equals sine theta, so the sine of 0 is 0, and the sine of pi over 2 is 1. We have our 2 out in front. We can integrate the next one, which is r to the 4th over 4. That's going to go from 2 to 5. Almost done. We have 2. Is when we plug in 5 to the 4th is 625 over 4 minus, then we plug in 2 in here. 2 to the 4th is 16 over 4 is 4. Then we can evaluate this next one. This is 1/2 times u squared from 0 to 1. Almost done. X 25 over 4 minus 4. Is 609 over 4. And then here we have 1/2 times U squared, 1 squared minus 0 squared, or just 1. It looks like this comes out to 609 over 4. Units cubed. All right. We'll do some more with polar coordinates next time. But I did want to kind of introduce that. So I'm going to send out an email with 2 things in it. One, the link for my lab hours tomorrow or today from 1 to 4:30. And then secondly, I'm going to send out that USub folder that has file that has the practice in it. Once I get this video today uploaded to YouTube, I'll send you the link for that. So what lab is due next Tuesday? Lab 7. Lab 7 is due next Tuesday. And I'm just going to skip over Lab 8. We're not going to turn that one in. So we'll turn in Lab 7 next Tuesday, and then Lab 9 will be due the following Tuesday. We'll just skip Lab 8. All right? Any questions? Okay, very good then. Everybody have a great day. Stay safe. I hope you have enough toilet paper. Probably within a few hours, Spencer, on the YouTube video. It just takes me a while to upload it. So however long that takes my computer to do it with the internet. All right. Have a good one, everyone. Thank you.